I mean, we heard interesting things. Thank you for presenting these things to your colleagues. I hope the other presenters would also be that initiative and show us interesting new applications of colloid science. So we have gone through capillary forces, capillarity effects, surface tension, wetting, and so on. Now we have to go straight for the major part of the course, major theoretical part of the course, which is interactions. So, in a way, a bit of a change from the previous lectures. I mean, we have to go through a long series of formulas, which are not that difficult, but you may find, of course, a little bit boring. In order to really get out something out of this lecture, because it's important fundamentally, just stop me at any point. Let's discuss what you see, the formulas, how you apply them, and so on, rather than just kind of like, if we keep this steady, I mean, you're going to get bored. I know that, but this is the nature of this material. We have to understand how van der Waals forces work. So this lecture will be an introduction to the molecular forces, discussion of various dipolar forces and interactions between polar molecules. From here on, the next few lectures would mostly follow the textbook of Izrelashvili. It's a very good textbook. It's the best textbook in different types of interactions. So I have put some chapters from Evans and Wennerstrom there, but these are really just if you decide to, if you find this material so kind of interesting that you decide to read a couple of books on the matter. Izrelashvili should be enough, and of course do follow the lectures, because I have tried to extract all the things that you need in the presentation here without the diluting formulas from the textbook. Now we're going to go through lots of formulas, but before we do that, we have this usually interesting picture which you have to explain. Now Ketan is not going to explain that, or Brian. What do you see here?
Growing wire.
Okay, well, you are not supposed to say that either, but anyway. What you see here is actually something that Ketan does in his research, assembling microwires from metallic nanoparticles in suspension by using dielectrophoresis, by using alternating electric field. And we're going to study dielectrophoresis later. So what you see here, these are the metallic nanoparticles which have, the original color should be pinkish, but I mean it looks kind of grayish here on that screen. You can see that the particles have accumulated in front of the growing microwire, which is the effect of the dielectrophoretic force. This is the electrostatic force which brings them to the tip. Now, what you see here is an assembly of particles. So this is really the equivalent of a microwire, which is assembled from nanoparticles. Inside this suspension, however, we have only nanoparticles and water. The electric field brings them together, and then they assemble into the microwire. But if you turn the field off, this microwire is going to stay assembled. Now, why is it going to stay assembled? Now, if we have nanoparticles, we have to use some fancy word, which would be nanoglue. So what is the nanoglue that holds the particles, the assembled particles, together in the microwire? If there is nothing else than nanoparticles and water. Okay, I mean, you're a spoiler here, really. I mean, like, yeah, right. Yeah. I mean, I know that you know, but yeah. The truth is that any colloidal particles in suspension would exhibit attractive forces, which are the van der Waals forces, and that's what we're going to start studying this lecture. But before we study the forces between particles, we have to understand what is the origin of these forces. Why do they emerge in the first place? And let's go to a little bit of a theory here. How do you calculate the interactions between two particles? Imagine that you could shrink yourself. You have these two particles which don't look very regular, obviously. They may not be even regular in terms of their structure. And you want to calculate the interactions between the particles. Now, how do you do that? Well, the solution here is that you're going to say, well, I'm going to do this by using integral calculation. I'm going to define a small volume of each particle. And then I'm going to study how these two volumes attract themselves. Then I'm going to integrate over all of the possible volume in the first particle and in the second particle. And I'm going to obtain the interactions which arise from the volume of the particles. Then there may be interactions which do not come from the volume, which come from the surface. For example, you may have charges on the surface. So then I'm going to define a small, differentially small surface patch on one particle and the other particle. I'm going to find how these patches interact, and then I'm going to integrate over all the surface of the particles in order to obtain the surface force. So then the interactions between the particle is going to be the integral of the molecular interactions in the volume over the whole of the volume of the particles, plus the integral of the surface interactions over the whole area of the particles. Now this is good, of course. It's very easy to write this formula, but obviously applying that is not that easy. So all that we're going to do from here on in the next 4, 5 or 6 lectures is going to be actually first understanding what's this term here, the small w, which is the interactions on a molecular scale. Where do they come from? And once we know where do they come from, once we know what is the dependence of these interactions on the distance, then we can integrate. Obviously, we're not going to integrate over particles of this type. We're going to integrate over simple particles, which can be spheres, cylinders, lenses, or just plain films. So we have to find formulas for these interactions, the molecular interactions, and we have to find formulas for integrating, so we can obtain the energy of interaction between the large particles themselves. When I say large, I mean large on a molecular scale. Obviously, they can be nanometer-sized particles. They're still going to be large in terms of molecular scale. So this is what we're going to do from here on for the next few lectures. Now, we want everybody to be on board here. So let me remind you some basic physics about. Now we always say interactions, and then sometimes we speak about force. Sometimes we speak about energy. How do force and energy relate in physics, and of course in the colloidal science that we study? This is a typical energetical curve for interaction between molecules. This is a typical force curve for interaction between the molecules, and the relation between them, this is very important, is given here. The force is the negative derivative of the energy with respect to the distance. Now we have the ultra fast thinking award here. You have, this is zero force or energy. You have these 3 intersect points. Now, which of those points is the point of equilibrium? Sorry? I hear what somebody say, like a bit loud. I hear like some RR, but not. You have RO, RE, or RS. Which is the point of equilibrium?
RE.
I hear RS. No, that's not the right answer. RE. Did you say RE? That's Chris. Well, now first of all, if you neglect the force curve, when is a system in equilibrium with respect to the energy? When you are in the minimum of the energy curve. When you differentiate the minimum of the energy curve, what you get for the differential of the energy is 0. So this means that in the minimum of the energy curve, the force is 0. You can define mechanical equilibrium as minimum of energy, or 0 net forces acting on the particles. So this is very illustrative. If the particles are closer, you see the force is going to be positive, it's going to push them this way. If the particles are, let's say, here, then if you check out what the force is going to be, it's going to be negative force in this direction. So it wants to put them back in the minimum.
Is that just, do people sometimes make an approximation that R0 is the equilibrium in their calculations?
This will be, it depends on, this will be for a more special type of energy minimum though. In many cases, what people will do, they would assume that the energy curve is like that. It goes down and then it just climbs up vertically. There may be a well here, square well. In this case, the point of equilibrium is going to be this one. But this is just because the curve doesn't have this slope on the other side. Now, we're not going to deal too much with this side of the curve. Now, this is quantum chemical repulsion. You just can't push stuff into itself. What we're going to deal is this part of the energy curve, which is the attraction. Why do materials attract each other? Whether particles, molecules, whatever. Any two molecules will try to attract each other. And before people have even understood the origin of the van der Waals forces, the molecular origin, which we're going to discuss right now, there has been this Lennard-Jones expression, which is still used very often these days. It says that the energy would be equal to a constant divided by the 12th power of the distance between the particles, minus another term, another constant, divided by the 6th power of the distance. This is the attractive term here, and this is the repulsive term. Why is the repulsive term has this 12th power of dependence? Again, because once you start pushing matter into itself, you have very high resistance. You can't push atoms or molecules or solid bodies together into each other. So that's why the moment they touch, the force, the negative force, the force which tries to separate them, the positive force actually in this case, becomes very large. And now we have this 6th power here, which has been derived empirically. They found that this is a good number. Now we're going to go through lots of pain just to see how this number relates to molecular interactions. What is the origin of this 6th power? And another slide of basics here. I have told this at least 5 times to the people in my thermodynamics class, and I repeated this again here, but this is very important. Now the kT is your measure of energy on the molecular or colloidal wealth. Each degree of freedom of a molecule or a particle or a human, if you like, brings with itself an energy of 1/2 kT. So your thermal energy on the average is 3/2 kT, or actually more. You have also rotational degrees of freedom. So you can calculate what is your thermal energy at any point. Obviously, it's too small to move you around, but it can move particles and molecules around. So when you have, let's say, an external force, which is going to happen often in our lectures, let's say in general the external force will be a difference in chemical potentials. In order to understand whether it's important or not, you always have this expression where you have the exponent of the external energy divided by kT. And the simplest formula for such type of expression is the density of air, for example, in Earth gravitational field. The density would be described by the density at, let's say, sea level. Then you have this term, which is the mass per molecule, gravitational constant, and z is this component, vertical, divided by kT. So using this formula, you can calculate why air gets to be thinner and thinner when you get higher. The gravitational force wants to pull it down. The thermal energy wants to push it out. If there was no gravitational force, the air would disperse into space by the thermal energy. Gravity is the one which brings it down to the surface. It is very similar, you can have this very similar in colloidal suspensions actually. You can take a cylinder with nanoparticles, and after a while these nanoparticles would distribute in this way. In some cases you can see them squashing on the bottom because the gravity is so hard with respect to the size, and in some cases you may not see them distribute at all because they're so small that their gravity actually is not important. Okay, so this is the basics thermodynamics which we need. Any questions here?
What is x1, x2 again?
What do you say x1, x2?
The top equation? X1 equals x2.
This is any thermodynamic parameter which relates to chemical potential. Density, concentration, essentially an extensive property which is related to the chemical potential. Pressure. You can write the same formula would be if you replace density with pressure, it's going to be, you can write the same formula for pressure and so on. Okay, so we have the basics, and then we can apply it to molecules. We have a variety of molecules and we have a variety of forces. And all of those forces contribute in one way or another to the van der Waals forces. The simplest force is between two charges, like two charged ions such as sodium chloride ions. Now, some molecules would not have a permanent charge, and these are most of the molecules actually, but they are going to have a permanent dipole. We'll define the dipolar moment a little bit later and so on, but they're still going to. The point is that you have to understand how the charged atoms or molecules interact with dipolar atoms and molecules. In the matter, you usually have many more dipolar molecules than charged molecules. So you have to understand how the dipolar molecules interact with each other. You may have a molecule which does not have even a dipole. It's absolutely electroneutral. Yet this molecule can be polarized. When you bring charge close to it, it's going to have a non-permanent dipole which emerges because of the electrical field around the molecule. So in order to understand how this works, we have to also understand how charges interact with polarizable molecules and how dipoles interact with polarizable molecules. The reason you have this difference here between these molecules and this one, now by this I denote molecules which have a permanent dipole moment, and these are molecules where the electron count is just redistributed because of the field. And finally, what if you have two polarizable molecules only, which do not have any charge or dipolar moment? Are they still going to interact? And the answer to this is yes. So when we go through that scheme, one step at a time, we're going to finish actually in the next class. We're going to understand how all those interactions work and how they affect the van der Waals forces, how they form the basis of the van der Waals forces that are important in any colloidal system. So let's start one force at a time. You don't have to remember all those formulas, of course. It's good to have them handy for different types of calculations though. But of course these formulas have been derived. Now what happens when you have two charges interacting? You have studied this in high school perhaps. This is so-called Coulomb's law of interaction between two charges. Now let's go through that formula and define all the parameters here and how you use them in practice in calculations. Now, Coulomb's law tells that the energy of interaction is going to be proportional to the charge of the first particle or atom or whatever, ion, times the charge of the second one, divided by 4 pi epsilon 0, which is a constant, and then the distance between the two charges or ions. Now in reality, if you have molecules, you calculate the charge by calculating the number of ionizable group on the molecules, or ion, or the number of charges on the molecules times the the charge of a single electron. So we have, let's say, a ion of chloride ion. The charge of this ion is going to be -1 times the charge of the electron, which is some constant. Now, how do you use in reality? Now, 4 pi comes because of, again, depending on the systems you use. You may go open a textbook, old textbook, and find that you're going to see the same formula without the 4 pi. This is depending on which type of electrostatic systems you use. In SI, you have 4 pi. Epsilon 0 is a pesky, long, unpleasant constant. You can find it on the second page of Izraelashvili when you need it. And then epsilon is the relative permittivity. Epsilon 0 is called the permittivity of free space. But it's really constant. It adjusts the dimensions. Epsilon is a relative permittivity, so it tells you what is the permittivity of the media with respect to vacuum or air. I'll go through some number just in a second. And then if we take the derivative of the energy, we're getting the force, which again includes the charges, these same constants, but already is dependent on the square of the distance between the charges. One formula that is handy is the so-called Born energy of an atom. What is the energy? What is the energy that you spend in order to charge an ion, for example, from non-charged state to charged state? What is the energy which you spend in order to kind of put one electron in or take one electron out? And this can be derived purely from electrostatics. The differential of this energy would be, like you can see, very similar to this formula. The charge times the differential of the charge divided by 4 pi epsilon 0, the radius of the atom. Then you can integrate this from charge 0 to the full charge of the ion. And you are getting this, which tells you this is the energy of an ion. This is the chemical work that you need to do in order to charge an ion or an atom. And I have this favorite, very simple. Once you know that, what you can do, for example, just to calculate something, what you can calculate is you can calculate the solubility of different ionic compounds. If you have sodium chloride, when it's in a solid, the positive ions are next to the negative ions and so on. What is the work that you need to do in order to dissolve that? You need to pull the positive and the negative ions together. Now, obviously, the ions would like to stick together, so you have to do work against that. On the other hand, however, once you pull them apart, you have the energy of the single ions being equal to the Born energy, which we just calculated. Then, the difference in the chemical potential when you put them apart would be the difference in essentially the energy that you generate to create both the positive and the negative ions here. You already know this formula, which tells you how a certain parameter relates to the change in the energy divided by kT. In this case, this parameter is solubility. So this is the energy of pulling two ions apart here. The solubility would be related to the energy of pulling two ions apart. And this is actually the most important thing that you need to remember here. The relation between the dielectric constant of different liquids and the solubility of ionic compounds, either sodium chloride or glycine is a small as a small amino acid. And actually the useful thing here, the one that you have to remember is actually what are the typical numbers for the polarizability of different liquids, for the dielectric permittivity of different liquids. So now what is the dielectric permittivity of water? It's about 80. Now, is water a good solvent for ionic compounds or not?
Yes.
It is. And now you know what is the reason for that on the basis of molecular basis. Water has high dielectric permittivity, high polarizability. So that's why sodium chloride would dissolve in water, but it wouldn't dissolve in, if you take here, these are some alcohols, propanols, butanol, and so on. Sodium chloride may dissolve a little bit, but it wouldn't like to dissolve in an organic liquid. So the dielectric permittivity, the dielectric constant of organic liquids is very low. What is the dielectric permittivity of air? 1. So you start from air 1, you go through a few numbers which are like 1, 2, 3, 4 for organic liquids, and then you go into the region of high dielectric permittivity. Methylformamide is kind of the winner here of about 200.
What's liquid mercury, do you know?
The liquid mercury would be infinite. Any metal, the dielectric permittivity of any metal is infinite. This is what makes electrons actually go through metal. So when you apply voltage across a metal, all the electrons from one side of the metal are going to go to the other side. There is absolutely no resistance for the electrons redistributing. So what is the reason of the permittivity in the first place? It is because the electrons in a molecule or atom would move towards the opposite charge. So liquid mercury would have an infinite permittivity, which does not mean, I guess, that you can dissolve sodium chloride in it. Possibly you can, I'm not sure. Okay. But the point is that you see that you should have, if you plot this on a logarithmic scale of 1 over the dielectric permittivity actually here, which appears here, you are going to get, and you have the logarithmic scale here, you are going to have straight line dependence, and it is very well confirmed by measurements. This was really an example of how you use ionic interactions in practice. Yeah.
When you melt the metal and you cool it back down, it stays a metal, right? It's not that everything just goes into that metal because it has infinite solubility in it.
Everything ionic. I don't know. This is a very good question. What is the solubility? I don't know what the solubility of sodium chloride in mercury. It's a very interesting. In principle, if you just follow this theory, it should be infinite. But somehow something tells me that sodium chloride does not dissolve in mercury. Now, there may be other reasons for that. Kind of in a way, in order to put an ion inside the mercury, you have to break the bonds between the mercury atoms. And I guess now mercury has an enormous interfacial tension. If you remember, mercury has an interfacial tension of 400. Now, in order to put the atom inside the mercury, you have to make essentially a small opening. So you create interfacial tension area over some area, which means that this is unfavorable. So I guess this may be the reason why sodium chloride does not really dissolve readily in mercury. Or it may, I don't know. You can check it out and let us know actually the next time. I like this question, such questions because, they are interesting. Certainly you're going to remember something out of this. And you're going to know about solubility, dielectric constant, and so on. You may forget the formulas, but you're going to know how the electric permittivity relates to different physical properties. And the reason we want to go to understand this now is because we're going to return back to this point when we discuss dielectrophoresis. All interactions caused by electrical fields in liquids are actually very related to these formulas that we're discussing here. Now, what happens when you have a molecule with a dipolar moment? Let's Again, thinking about different molecules. Now I have drawn here, excuse the appearance, but that's what you can do with this pen. I have drawn here tetrachloromethane and trichloromethane. Now what do you think is going to be the dipole moments of these molecules? The answer is on the next, okay, don't look down, it's on the next sheet. But just kind of think about these molecules and try to tell me, is there going to be some difference in the charge of these molecules compared to on the molecular scale? You know that methane has 4 symmetrical bonds all around the carbon. You have 3 chlorine ions here, and we have 4 chlorine ions here, and we have 3 chlorine atoms here and 1 hydrogen. Now, which may be polarizable, which may be not? What is the dipole moment of those molecules and so on? Some guess?
Trichloromethane will be polarizable.
Right. It's not only polarizable, it's polarized. So this is a very symmetrical molecules. Now the chlorine ions always would like to pull electrons towards themselves. But they pull it symmetrically, so there is no distribution of negative and positive charge. In this case, however, the chlorine ions pull electrons. The hydrogen atom, if you remember, is readily giving away electrons. So then this is going to be positively charged, and this part of the molecule is going to be negatively charged. And if you want to describe this mathematically, you then define dipole moment, which is equal to the charge times the length between the two charges. Now, why do we have 2 charges here and 1 charge here? You have plus minus Q and plus Q. Why don't we have like plus or minus some, like, twice Q or something like that? Because Q is equal, minus Q is equal to plus Q. So if you look from the molecule from far away, it's an electroneutral. If you come close to the molecule, you find out that one of the sides of the molecule is more negative than the other. Now the dipole moment is defined, you can work in coulombs per meter, but then you're going to get numbers which are going to look terrifying. So that's why people still use Debye. Now when you work with Debye, you have numbers which are 1, 2, 3, 4 and so on. When you work in coulombs per meter, you have a numbers which looks like 3 times 336 10 to the minus 38. So that's why actually the CGS system is preferred in many cases. Some practical examples. What do the dipole moments of different molecules look like? Here are the molecules which we just described. Tetrachloride, 0. This one has should be this one, 1, which is not a small dipole moment. And you can go through different molecules. You can see how the molecules which have more electron active entities or are more asymmetrical have higher dipole moments. Ammonia, sodium chloride, cesium chloride has an enormous dipole moment. Why? Cesium chloride has a higher dipole moment than sodium chloride.
Why?
Why?
Because the electronegativity of cesium is very low.
Really? Like in both sodium chloride and cesium chloride, you have fully charged negative and positive ions. What is different here?
Size.
Size, right. Cesium is an enormous ion, means that the positive and the negative charges are further apart,
So it's a big L.
and the dipole moment is equal to the distance times the charge. So this one comes from the distance actually between the ions. The other ones come from the symmetrical molecules. Water is faring fairly well here, but it's not extraordinary. So there are some other reasons for the polarizability of water here. And you can actually, if you don't know the polarizability of a certain molecule, the dipole moment, you can actually calculate it by knowing the dipole moments of the bonds and then adding them in a vectorial manner times the cosine of the angle. Okay, so now we know why molecules can have dipole moments. Now what happens then if you take a molecule with a dipole moment and bring it close to an ion? Now first let's say what happens if you have a molecule with a dipole moment that is very far away from an ion? Nothing. I mean, that's true. The reason is that from the viewpoint of the ion, if the molecule is too far away, it sees a positive charge and a negative charge, but they are about the same distance and very far away. So the ion doesn't care about that. Now, however, if you take this molecule and bring it closer, and let's say tilt it at some angle with respect to the shortest distance here between the ion and the molecule. So this is the ion. It has a charge of Q. This is the molecule. It has a charge of plus Q and minus Q on the two sides. Now you bring it closer and they start interacting. Now you can say dipole or not dipole, I only work with interaction of charges. I know Coulomb's law. So why don't I say, let's say take the interaction between the ion and this part of the molecule, and then the interaction between the ion of this and this part of the molecule. Sum them up. One is going to be positive, the other one is going to be negative. The ion is going to attract the oppositely charged end of the molecule and is going to repel the similarly charged other end. So then what you could do is I can use the Coulomb's law. This is the permanent part of the Coulomb's law, charge times charge of the ion times charge of the one side of the molecule. Distance between the ion and this part and distance between the ion and that part. And we have to subtract them because they work in different directions. Now what follows here is just simple simplification and calculation. You can say, well, if they are not too close, then I can approximate this distance with this distance. And similarly, I can approximate this distance with this distance. The distance from here to here is equal to this distance, which is the distance between the ion and the molecule altogether. R. This is how we define the distance between the ion and the molecule. Plus this small side of the triangle here, which in itself is equal to 1/2 of the length of the molecule times cosine theta. So you plug in these expressions here, you do the math, you find out that the energy of interaction between the ion and the molecule is equal to the charge of the ion, the dipolar moment of the molecule, cosine theta divided by 4 pi epsilon epsilon 0 epsilon times r squared. Now why you aren't we surprised of these constants? Because they appear in all electrostatic things. One thing, however, that's important is compare this with Coulomb's law. What's the difference with Coulomb's law? Right. Now then which interaction is going to be long ranged? Coulomb's interaction or dipole ion interaction? Coulomb's, right. So if you have two ions, they interact from far away. If you have an ion and a dipole, they interact for a shorter distance. You can see that the decay length kind of is much shorter.
So R is the distance from ion to
Right, I mean R is defined like the distance between the center of the ion and the center of the molecule.
Should those
It should be R greater than L.
Which one?
If L on the slide, it should be R much greater than L.
Okay, oh yeah, right. Yeah, that's true. This should be R. Okay, I'm putting just is greater than L. Yeah, sure. Put it the other way. So this distance is much larger than the size of the molecule. If you have it the other way, if the molecule is here, it kind of gets to be complex. I mean, it's really calculations there are not straightforward, but then that's not a common place in reality too. So this is R and this is L. Just to make this even simpler, if you take these expressions, you're going to find out, if you check the physics books, you're going to find out that this expression is actually the field, the electrical field generated by an ion at distance r away from the molecule. So you have the formula which tells you that the energy of interaction is going to be equal to the field times the dipole moment times the cosine of the angle. So the second distance, now you may forget how do you derive this, but I want you to remember what's the distance, well, what is the difference between these formulas. What are all those cosines, r's, and so on, which obviously we don't like too much to see them. But why do they emerge there physically? What is their physical reason? So the first important physical point here is that the interaction here is shorter ranged. You have to bring them closer in order to have the same energy. The second one is that the interaction is dependent on the angle. If the molecule is directly like that, what's going to be the interaction?
0.
And it's going to be 0 y physically. I mean, it's going to be 0 by the formula because cosine theta will be 0, right? But what is the physical reason that if the molecule is like that, it's going to have 0 interaction with the ion?
There's a much attraction as a repulsive.
Here?
Theta is 90. Theta is different with respect to thickness.
Yeah,
Theta's 90 there, okay.
yeah, no, the cosine theta is 0 like that.
No,
Yeah.
There's a special.
That's theta is 90.
Anyway, cosine theta is 0 when you have an angle of 90, right? So,
cosine is a 0 is 1, cosine of 90 is 0.
right.
Yeah, so theta is 90.
Okay. So anyway, what you're going to have here, I mean, going back to the cosines and so on, what you're going to have here is 0 if the molecule is directly perpendicular to the axis between the ion and the molecule. Now, what's the physical reason that there is no interaction? Right, the charges are balanced. The positive charge on one side and the negative side on the other charge on the other side interact equally with the ion. One is repelled, the other one is attracted. So net force is 0. So in this case, you only have interaction when you have some angle of rotation of the molecule.
So is
No, he was first. Sorry.
Was it said you didn't give a moment. I mean, that puts a torque on the molecule, right?
But it's far from
So-
Yeah.
Very good point, and we'll discuss this later. I mean, I'm glad to hear that. So, kind of, for me, it's a good wake-up question in the sense that, I mean, we're going to discuss this in a second.
Is that because L is small compared to
Uh,
R? Or whatever.
yeah, well, I mean, this is. I mean, like you can calculate this for any distance, but this is the way to obtain this easy expression. Now, his question was essentially, now is this going to make the molecule kind of want to turn itself towards the ion on the oppositely charged side? And this is a very good question, and we're going to discuss this in a second. I mean, actually, obviously, you can't calculate the force which is dependent on cosine. You want to remove the cosine. So we're going to derive an expression which actually tells you how much the molecule is going to orient itself and what is going to be the average interaction between the molecule and the ion. We're going to average that over the angle, and I'll show this in a second. But before that, what happens when you have two dipoles? You can, if you're a lover of long, tedious calculations, you can do the calculations at home. I'm going to give you the result here straightforward. Now, in this case, if you just consider how this plus interacts with this minus, how this plus interacts with this minus, and so on, how this interacts with this, You have 4 interactions here. You can define 3 angles. One angle of tilt of this molecule with respect to the horizontal. One angle of tilt of this molecule and one angle of rotation of the second molecule with respect to the first one. And then you have this complex expression of the energy of interaction as a function of the first, second, and the third angle and the distance. And you can tell me now this is a totally useless expression perhaps because we don't know the angles, and anyway people have derived that. Now there is something that especially people who are interested in dielectrophoresis can immediately derive out of this formula. Now imagine you have 2 dipoles. Ideally I would have 2 dipoles of similar type. Now if you can see this, let's say this is the negative charge, this is the positive charge. So this is one dipole and this is the other one. Now obviously the dipoles would like to interact like this is going to be a good interaction, the positive facing the negative. Now you can think of 2 very favorable interactions. One would be the dipoles are like that. The positive side faces this negative side and the positive side here faces this negative side here. The other interaction would be the dipoles like this. Now which of those interactions is stronger? This one or that one? The first one? Okay, anybody for the other one?
I'll vote for that one.
You know the answer, huh? You go to that one. Yeah, the answer is actually the other way. You can just immediately plug the data in this formula because you have cosines and you can put them online. So these are essentially the energy of interactions here as a function of distance for the interaction when the molecules are like that and when the molecules are like this. You can see that at a certain distance, the interaction when the molecules are, now this is negative. Negative means favorable, attractive. You can see that at a certain distance, the interactions when the charges are like, the molecules are like that, is always smaller than the interaction when the molecules are like this.
I thought that this one was somewhat of a metastable state.
Yeah, well, no, it's just kind of what happens if you put them like that and held them. And actually, this is not only theoretical question because this is the chaining effect which we're going to study in dielectrophoresis and which is the basis of magnetorheological and electrorheological fluids. This can be, I mean, we're going to discuss these fluids. Fluids would change their viscosity as a function of electrical field. But the answer is like that. If you put them like this, you have favorable interactions on the ends. But you have unfavorable interactions because these opposite charges are too close. So they're favorable here and here, but they are disfavorable like that. So the molecules would really like to be like this. So any oppositely charged sides are actually as further apart as possible. It's the like charge sides of the molecules are further apart as possible, which is not the case when they are like this. It is counterintuitive. I mean, if I would think immediately, I would think possibly the other one is more favorable, but that's how it works. Okay, so now we know this. Now the question is, actually this is the question what Chris asked here, and you're not going to laugh. He's not going to be very popular by the answer that I'm going to give. Because right now we have to go through some of the biggest formulas for this class so far. And this is like that now. You can say, okay, this is your charge. Now we know what happens when the molecule is at different angles. In reality, however, the molecule would always have thermal motion, so it's going to tumble all around. On the other hand, if it's oriented like that, it's going to be attracted to the charge. If it's oriented like that, it's going to be repelled. So you're going to have also some additional tendency for the molecules not to fumble freely, but to kind of like prefer fumbling when this end of the molecules faces the ion in a favorable way. So then, now you say it like that, I don't know and I don't care how the molecules fumble. I want to understand what is the average interaction. If the molecules rotate freely and if it interacts with the ion, what is the average interaction between the ion and the molecule it's expressed as only as a function of the distance between the ion and the molecule. And now you remember the formula. How do you compare an interaction against the thermal energy? You have to divide. So now let's say like that. Now you want to know what is the interaction between the molecule at any angle, which it may assume during the thermal kind of rotation and vibration. You can say like now this interaction, the exponent of this interaction is one which I know. That's how I calculate the effect of the field. Then if I take the effect of the field at any angle and integrate it over all possible angles, and then normalize this, because I have to, this is just normalization because you have to kind of essentially a factor which appears by integration over all possible angle. I'm going to obtain essentially, this is the average of the interaction at all possible angles compared against the thermal motion. So when you do this, this is essentially the average of all possible configurations are going to give you the energy of interaction without the angle, because the angle is going to be averaged, and you're going to take this into account automatically when you do the averaging. Now this integral is obviously no fun to calculate, especially with the exponents. Exponents are always a problem. They don't integrate analytically. So what people have done with a good enough precision, and you can follow all the derivation through the book of Izraelashvili. I have just sketched it here. So you follow what's going on without too much. Now you can say exponents can be expanded in series. So I can expand the left-hand side and the right-hand side. I still have to take the integral of the right-hand side, but I can take only the first term. Substitute here the energy at different angles by the energy which I have derived already. This is the energy of ion-dipole interaction. So putting here the energy of ion-dipole interaction as a function of the angle. Integrate it over all possible angles, like shown here. And when I do that, I'm going to obtain actually what is the angle averaged energy only as a function of the distance. In order to do this, however, I have to assume something. And what do you have to assume in order to do the expansion here? Right, you have to assume that the energy divided by kT is less than 1. And I'm going to torment you. The question is, what is the physical meaning of that in a second. So you can start thinking about this if you like, but let me give you the answer for the integration first. So right now I have this here which shows that this is already freely, this is really molecular interaction. You can allow it to move around in any direction it likes. And it's really going to move around in any direction because of the thermal motion, but it's going to prefer some directions. And this is going to lead to some interaction, which can be, if you integrate the previous expression, is equal to this one. At the assumption that the kT is larger than the highest interaction energy in the favorable configuration, which we needed in order to do the expansion in series. And now you have even more constants here, so this doesn't look very nice. But then if you just compare this term, this energy, with the energy of interaction of ion and dipole, when you know what the angle is. So this is the energy of interaction between fixed ion and dipole, and this is the energy of interaction between freely rotating ion and dipole. Now what differences can you see here, and how can you explain them? First of all, I mean, like any time I ask you this question, you look at the exponent here over r. The first thing that you can see is that when you do this in a molecule and you let it rotate freely and so on, suddenly this dependence becomes even weaker. So it's the molecule which fumbles around because of thermal motion is going to be attracted even less strongly than a molecule at a fixed angle. Now forget the constant scale. What is the other difference that you see? Right. So right now in this form you already have KT, which shows you that this interaction is temperature dependent. Why is it temperature dependent? Because temperature is the one which causes the thermal motion, right? So in a way you inserted the temperature here, KT. The thermal motion acts against the, actually if there is no thermal motion, let's say this is the ion, this is the molecule would align like that and attract itself to the ion. But because of the thermal motion it doesn't do that, so the interaction gets to be weaker and it's temperature dependent. Now, all of this was derived from the assumption that KT is larger than the energy of interaction. Now, what is the physical meaning of that? Now, before we do that, let's discuss the other case. Now, let's take the case where KT is smaller than the energy of interaction between an ion and a dipole. And you say, like, what happens? Let's say, let me calculate this for a single charged ion in water. This is the parameters. The charge is 1 electron. This is the dipole moment of water, which is the polar molecule. This is the epsilon of water. You can put this and you are going to obtain that this happens at a distance between the ion and the water molecule of 0.2 nanometers, which is about 1 molecular distance. Now, what's the physical meaning of that?
You can't go smaller than that.
In distance? No, I mean, like it's, you can perhaps. It's about a smaller size, but I mean, it tells you that even when they are 1 molecular distance apart, actually this is not well fulfilled. So what happens if KT is smaller than the energy of interaction? The thermal energy is smaller than the interaction energy.
Will it lock in place?
Right, exactly. So if the thermal energy is higher than the energy of interaction, the molecule would rotate freely. However, if it's smaller, then the molecule would lock in place. And this is the reason for something which you have heard certainly about, hydration. You know that the first layer of water molecules around an ion is actually in a way immobilized against the ion. They don't move around.
In your derivation of that equation, you assumed it like a far field anyway for the angle.
Right. No, I mean, like the equation that we derived in the previous, it just tells us what happens when they are far enough away and the interaction is not too strong. Now this, if you have to derive the interaction here, it's going to be a little bit different, but you can just say like that. Now let me just take the other case. What if this criteria was not fulfilled? And you can see that this is the other, actually when you do that, you can see that the other estimation was not that bad, because it's not fulfilled only for the first layer of water molecules. So the second layer of water molecules are already going to be freely moving around. So because of this reason, actually, you have an ion. The first layer of water molecules is immobilized on the surface. Any other water molecules are not immobilized. If they were immobilized, let's say a very far distance away, then when you put ions in water, it's going to freeze, right? It's going to stop being a liquid. So the fact that water is still liquid when you put ions in it tells you that the other condition, the reverse one, is fulfilled for most of the cases, except for the first layer of molecules around an ion. A protein molecule, a surfactant molecule, and so on. And this has very important consequences for short-term forces. If you bring two ions together, or two surfactant molecules, then you have to disrupt the water layer around them, and I mean, we'll see what happens then. Okay. Any questions so far?
No, I mean, we're saying they're rotating freely, but we're not putting any weight at all on the angles. So it says we're...
No, we put an end of the angle. We did. Because we have here, we put the angle-dependent energy.
But aren't we assuming that all angles are equally likely?
We assume that all angles are equally likely, but the energy here would be attractive in this case. So it's in a way it's self-adjusting. So it tells you what would be the preferred molecular orientations when you do this calculation. I mean, this is just statistical molecular thermodynamics.
But to be right, would you have to put the weight on, okay, one orientation is more favorable? So that means that angle is going to be at the weight more?
We have to go through molecular thermodynamics, but actually this is how it works. I mean, it actually, the weight is automatically included when you do this calculation. So in a way, this calculation calculates that the molecule is going to be more likely in this configuration rather than in this one. Just because in one case the exponent here will give you a large number, in the other case a small number. So what will happen is actually when you do the calculation, it tells you that the molecule is more likely to be like that than like this. The lower the temperature, the more likely it's going to be like that. So it automatically averages actually the preferred and the non-preferred, not averages but weights the preferred and the non-preferred orientations. I mean, this is really a form of statistical thermodynamics. I didn't want to go into details here, but that's how it works.
Which part of the part is
Right. This is the rotational thermal energy.
So, okay, so is this an example of where the rotational part is quantum instead of discrete number of positions?
No, in this case, I mean, like these calculations are made without the discrete number of positions. Now, if you want to do this precisely, let's say you are a molecular thermodynamics guy, then you're not going to average over all angles, you're going to average over all quantum possible configurations. Although rotational component, I'm not sure whether it quantizes specifically or not. I mean, when you do quantum chemical calculations, you go one level further, you know which is the specific angles because the angles would quantize. This is very simple statistical thermodynamics without quantum effects here yet. We're going to discuss a little bit of quantum chemistry the next time just because of the van der Waals forces. But right now this is just molecular thermodynamics.
I mean, but it seems like the position of the molecules is very discrete.
Well, I mean, the truth is that the molecules would, right now what you have done is you have calculated which molecules are going to be immobilized. Now you don't calculate the position of the molecules. But this immediately tells you that the molecules which are at distance 0.2 nanometers apart are going to be immobilized. You haven't calculated any position or something like that here. In order to do that, you have to go into quantum chemical calculations, calculate how they pack, how they repel, how they attract, and so on, which some people do.
I mean, normally it's when you compare the energy to KT, if it's comparable or less than KT, then it's got quantum dependence, right? So, I mean, this
Well,
case,
yeah, any energy would have quantum dependence, but in this case, you can say, I mean, I don't care about quantum effects yet. I assume that the energy is continuous. And in many cases, this is a very good approximation because, as you know, in many cases, the quantum levels are so dense that maybe the angle, for example, quantizes, but because it quantizes in so many different configurations, it's actually as if it's almost a freely rotating angle. So quantum effects are negligible here as a first approximation, and it works very well. Now, if you want to say, oh, no, I want to understand how the water molecules orient themselves, then you go and you do the quantum chemical calculations, you see where each molecule is situated, some will be further out, some will be... So there are lots of things to do. You have to think also about electronic effects and so on. But this formula just tells you if the molecules are closer than 0.2 nanometers apart, they're going to be immobilized. How they are exactly immobilized is something else. I mean, you don't calculate this here. On the other hand, you know that if they are further out, the water is going to stay liquid, which is good. So that's the reason why when you put sodium chloride in water, it does not freeze. Just, okay. Yeah, we should move on, but yeah.
I want to move on.
Okay, let's move on. You can ask these questions later. I mean, this is a very kind of rule of thumb calculation, but you can immediately see the power of, let's say, dipole-ionic interaction and so on. Just by knowing the interaction and comparing this with KT, you can find some things which are very basic for colloids, biological systems, and so on. Okay. Now I'm going to give you directly the angle average formula for two interacting dipoles. You can go through the whole, I mean, in this case, as you can imagine, the calculations are even more complex. You have to average over three angles. But when you do the averaging over three angles, you get this formula, again, for the case when they are farther apart from the thermal forces to really freeze, so that they just move freely. Now, tell me, what do you like in this formula? There is something that I like a lot. Now, what do you like? Artie was about Right. Right. I mean, this is one way you can say, because any two molecules would be, or almost any molecules could have dipolar moments. This is the first time we already justified the 6 power in the Lennard-Jones potential. So, I mean, it may have been fitted originally, but right now there is a molecular justification for the 6 power. And before we finish, I would really like to go a little bit further here and just discuss polarization effect, just to kind of set us on the way for the next week's lecture. So right now we discussed that the molecule has a dipolar moment. Now what if it doesn't? Does this mean that this molecule is not going to interact with anything? Or does this mean that there is some way for this molecule still to interact?
Is it a polarization?
Right, so the molecule can be polarized by another molecule. So even if it doesn't have a dipolar moment, it can become polarized. And this is an explanation of how this works if you just take a hydrogen atom. Now, typically, let's say the negative electron is going to retain the gap around the positive nucleus. And the net dipolar moment of this is going to be 0. However, if you put this in an electrical field, what will happen is that, let's say, this is the positive side of the field here. The negatively charged electron would like to come closer to the positive side of the field. The positively charged nucleus is going to get further away. So then, because of this, actually the way the electron is going to start rotating is going to be further away from the nucleus. Now, if you project this vertically, you are going to have this distance L, and you are going to have plus an electron and minus an electron. So effectively you have a dipole. This is not a permanent dipole. If you remove the field, it's going to go away. But you still have a dipole, and this dipole can still interact with the field that causes it, or the ion. You can have an ion here. So because of this, an ion, for example, would polarize a molecule, and then it's going to interact with the polarized molecule. Just something that you would like to know for many cases from here on. The polarizability of molecule is proportional to the volume times the electronic polarizability of the molecule. So just kind of, it's important to know that the volume of the molecule is always included here. And the polarizability has obviously a complex dimensionality, but of course once you start using it, you don't care too much about that, as long as you use the right dimension. So this is the reason. I'm not going to go into all details right now. We're going to study this formula the next time. I think you have had enough formulas for today. And to really have a very few formulas to finish these molecular things. What I want you to remember is that an ion is going to polarize the molecule, and then it's going to interact with this molecule. Just want to finalize on the polarization of molecules. We have this kind of forced polarization. And we have eventually a molecule may be dipolar, but as we discussed, it's going to rotate with a preferential orientation, like weighting. So this is called orientational polarization. And eventually you can say that the full polarization of the molecule as a function of the field is going to be the sum of the electronic polarization and the orientational polarization. This does not mean that any molecule has those two components. Some molecule may have only electronic polarization if it doesn't have a dipole at all. Another molecule may have only orientational polarization if it's very hard to polarize, but then it has a dipolar moment. Typically molecules would have both. So you have a dipolar molecule, you put it close to an ion, it starts rotating with a little bit of preferential orientation towards the ion. And then because the ion also polarizes it, you have some additional polarization which comes because the molecule is polarizable in the field. Now, well, you can tell me, well, you're discussing effects which seem to be subtler and subtler. Like we started from the ion-ion interaction, which is so strong, and we went to some interactions here which just come because the electrons are kind of slightly displaced and so on. But the reality is that the most important interactions on a physical scale are the ones which come from polarization. This is, as we're going to see the next time, this is the core of the van der Waals interactions. And it is the core of the van der Waals interactions because very few molecules are charged. Not all molecules are dipolar. But any molecule is polarizable. So it's kind of essentially, in this case, quantity versus quality. The quantity of polarization beats the quality of ionization or dipole, if you like this. Now, in conclusion, just the summary slide. You can find this in Izraelashvili, and I would recommend that you mark this page and check it out from time to time. This is really the basics of lots of what's in Izraelashvili. Now, these are all types of molecular interactions summarized. The complex covalent metallic interaction is not something that we don't care about because you don't find it in colloid systems. In these lectures, we went through what happens through charge-charge, what happens through charge dipole, and these have two cases, fixed dipole and freely rotating dipole. So we derived both of those formulas here. Then we discussed dipole-dipole interaction. I gave you the formulas for fixed dipoles and for rotating dipoles. And we discussed some polarizability issues, which in the next lecture are going to carry us through the rest of the interactions which are related to polarization. And there are some more complex interactions like the hydrogen bonding, which are going to emerge later in the class. So we are more than halfway through the molecular interactions. We are going to go back to the colloid system starting from the next class. Let's finish for now, unless you have some questions. No questions? Okay, then we're done.
Okay.